Good morning, everyone. Today, I will be speaking about one of the most fascinating subject in today's science, that is about the planets in the sky. You must have seen planets in sky, where you see the nuclear sky, Saturn, Jupiter, Venus, Mercury, all these planets you see. So, question comes in your mind that if there is any other planet in the sky. And today we are going to explore this question in my talk. So, as you see, in our solar system, there are 8 planets, and from this picture, you can see that there are 4 tiny planets. That these are the rocky planets, and this is Mercury, Venus, Earth, and Mars. And then there are 4 big planets: Jupiter, Saturn, Uranus, and Neptune. So these are called gaseous planets. So uh, we have a different variety of planets, and all these planets are revolving around the sun. They are having the different orbital period, and as we know that life exists in only Earth, not in other planets. So in that sense, it is unique. But question is whether our solar system is unique, whether there are many other systems like our sun where planets are rotating around these stars. So yeah, so as you can see in this picture of Milky Way galaxy, our location, the position of our sun is given here. It is a tiny point, whole solar system where our sun as well as all these planets are there. It is a tiny object in the scale of galaxy. And note that there are so many galaxies. So, and there are so many stars in galaxy itself. There are billions of stars. So, what is unique? Why there is only life in Earth? Why our system is unique? So this question comes in mind many times, and as a layman, even general public thinks about this, that whether we are unique in this universe. Forget about the galaxy, because there are billions of galaxies, there are billions of stars in each galaxy. So there are huge number of stars. So you see, sun is just one average type star. Among all these stars, billions and billions of stars are there. Sun is just one average star, means there are many massive stars than sun, there are less massive, there are many bright stars than sun, there are fainter. We have different scales, but life is there as we know right now. So question is there whether there is any star where we have this planetary system other than sun. So I will focus my talk on this today. So when we say planets around other star, it is called extrasolar planets or exoplanets. So my talk is focused not in our own solar system, but in the extrasolar planet or exoplanet that are rotating around other stars. So as you see, this is difficult. As you can see in this picture, a planet is in front of a star. It is like Jupiter in front of the sun. So it is a tiny piece of object, very tiny, as you can see here. And sun is our star, so nearby. But all these stars are farther and farther, like this one. So because in star, the distance is in millions of light years away. So they are very far off objects. You will not see stars like this in the sky. Okay, you will see star farther and farther. When the star goes farther and farther, these become smaller and smaller. So you put the star further and the star becomes smaller. And you again put the star further and you will see the star smaller. And then you have this kind of structure in sky where star is quite far off. As you can see here, our own star which I was just showing, it becomes fainter when you push it further away. So this is still a bright star. There are many faint stars. So most of these stars are quite far away, though it also depends on the luminosity of the star. But in general, if a star is really faint, it means it is very far off from our position. So as you see here in the previous slide, you hardly see a planet. Earlier one, you can see this planet quite easily, quite clearly, and when you push the star further, it is fainter. I mean, very difficult to detect this planet in front of star when a star is such huge. And now we have pushed the star further away, and it is extremely difficult to find that black spot in the star. So, and you push the star further away, and now it is extremely difficult. You cannot see that black spot in front of the stars. So planet is like this. So they are distributed in the sky, but they are very tiny object. You can't see them. It's extremely difficult to detect these planets in this kind of scenario. So see, looking for planets have been going on since long time. People were always curious whether we are alone in this universe. So they look into the sky and try to locate these objects. They think about the planets and all the stars, but it is difficult to see the star itself. They are very faint object. In a clear sky, you hardly see more than 6,000 stars. Even that too from very good sky conditions, very good atmosphere, no dust, and you have to uh, adopt your eye in night sky for about 30 minutes, then you can see of the order of 6,000 stars. But there are thousands, millions and billions of stars in the sky. In our galaxy only, then there are so many other galaxies. So people have always been curious whether there are other planets in the sky. So this Peter van de Kamp, he sort of proposed in 1963 there is a planet around a star. He reported this and he claimed that it is a 1.6 times mass of Jupiter. This star is rotating around the North Star. So this is a nearby star in the sky. But this claim was found to be false in 1974 and we rejected if there is any planet in the sky beyond our solar system. And the second claim, sort of claim, came by Smith and Tell in 1984 when they say that they have seen the disk around a star, and it is believed that these planets are formed in these disks. Though they didn't claim that there is a planet, but they claimed that the formation of disk and they imaged that disk, as you can see in this picture. So there was some, indirect hint that there could be a planet, but there's no such reporting. And first discovery of the exoplanet came in 1992 around a dead star, that is pulsar, which is a sort of neutron star which rotate quite fast with a speed of millisecond, and then we receive the pulses frequently. So this is very tiny leftover after the death of star. So they discovered this planetary system around the pulsar. But pulsar, as I said, I mean, it is dead star, not normal star, which we see in the sky. So it was not that much interesting. People were, looking to find the star around sun type, to look for planets around the sun type of star. That is a sort of main sequence star of our sun type star. So in 1995, first genuine discovery of exoplanet was reported around a solar-like star 51 PSC by Meyer and Quelich using a small telescope. But they used a technique, and why they could discover that planet, because they have very sensitive instrument. So the first exoplanet was discovered, named 51 Peg B, because it was rotating around the star 51 Peg, and the planet was slightly bigger than Jupiter. As you can see in the picture, it was slightly bigger than Jupiter. So it was first major discovery of the exoplanet around a star outside the solar system. And just to tell you that in 2019, they were awarded Nobel Prize for their discovery, for their finding of exoplanet around a sun-like system beyond the sun. So it was major discovery at that time. It opened a floodgate, and after that, similar type of work started, and a lot of exoplanet discovery were reported. But there were some issues with the radial velocity detection which they were using, that you cannot determine the precise mass of the planet. You can give a lower limit but not the precise mass. So in 2000, Chervenu and Henry, two different groups, they were leading their groups, and they reported a transiting exoplanet. So I will tell what this transiting exoplanet later slides, but they detected a planet when it was passing across the disk of its sun. So as you have seen, and many of you must have seen this Venus transit, when Venus is going in front of the sun, and you see a small dot passing for 2 hours. Some of you might have seen the Mercury transit also. So it is same. When we say transit, means a planet is passing across the disk of the star. So they discovered first transiting planet and reported the mass of the planet, and it was just 0.69 times massive than Jupiter. So it was smaller than Jupiter mass, and it is very small orbit, 3.5 day period orbit. As you see, Jupiter, our own Jupiter, has quite large orbit around the sun, but it has just 3.5 day orbit. It is very small orbit in comparison of Jupiter, and it is just slightly lighter than the Jupiter. So after that, these discoveries, whether that 95 radial velocity variation around the 51 peg or transit variation around as 209458, it has opened the floodgate. A lot of interest was generated. People have spent their time to discovering for the exoplanets. A precise instruments, dedicated telescope were focused towards these nearby stars to look for the planets. So planets discovery, it's just 25 years back. People are searching for hundreds of years. So why they could not detect the planets? What is the problem? Because planets are faint objects. These planets do not emit any light by their own, like the stars. They emit the reflected light. So the star radiates and its light falls from the planets and then it reflects and reaches to us. So we see these planets. So like in case of Jupiter, Saturn, Venus, all these are shining because of reflected light. I mean, the sun's light is falling on them and we can see them. If you see the further object like Neptune or Uranus, they are quite far off. Not much light is going there from the sun. So we cannot see them without a telescope. So these are faint objects and the star is quite bright in comparison of the planet. So even as I've shown in the previous pictures, a planet is near to a star, we cannot see it because the star is so bright. So how we detect these planets then? There are some methods. Of course, direct imaging is one technique where we try to detect these kind of systems where there is star and planets. There are certain limitations, but I will explain it in my next slide. But there are other methods. Other is called Doppler method, which is radial velocity variation, through which the first exoplanet 51 Peg B was discovered, and the transit method, through which SD209458 planet was discovered, and then there is Microlensing technique also, through which we can detect. So I will go one by one. So what is this direct imaging? As the name suggests, we are trying to see the planet directly, but it's not that much easy, because if you see this lighthouse, if there is a firefly very close to this lighthouse, you cannot see this firefly, as you can see the previous picture, because in the glare of the light of the star, or in this case the power lighthouse, this firefly is negligible, its light is negligible. But if you somehow block the light of this powerhouse, then you can see a dot, as you can see in this picture. So we have this thing here, small dots. So you can see there is a tiny firefly, and large version is shown on the left side of that dot. So what does it mean? That you have to block the light of the star to see a planetary companion, a planet around that star, nearby planet. Okay, so this is called direct imaging. So we need very high sensitive instrument and high angular resolution of the telescope to see these planets near the star. So as you can see in this picture, in 2008, first detection of the exoplanet, direct imaging technique, and this is called coronagraph. Star is blocked, and when you block the light of the star, you can see that there is a tiny dot, and that is nothing but a planet. Okay, but we needed a big telescope, like 8.2 meter, very large telescope in Chile. Chile has one of the best sky in the world, and all big telescopes, if not all, most of the big telescopes are in Chile. And it is such a huge telescope, 8.2 meter diameter telescope. It needed a special coronagraph to detect this planet. And later, HST, Hubble Space Telescope, detected this planet, as you can see in the lower picture, the tiny variation, because its planet is revolving around a sun, means it's a star, it will move and it will complete a cycle in its one orbital period. Okay, so if you monitor like this star 2 year time, it moves from its place because it's revolving around, it's a star. So HST could image this planet Beta Pictorius in given in the lower diagram. It is 1,000 times fainter than its host star, and distance of this star is 9 times greater than the Earth-Sun distance, which is 1 AU. So it is 9 AU distance. So in that sense, it is quite far off. As you see in earlier cases, 51 Pegasi 209458, they were very close to their star. The planets were very close to the star, but in this case, planet is quite far off from its star. So it is rotating. It is revolving around the star in a quite longer period, like our Jupiter and Sun, Neptune, Uranus, all these planets do. So but if you monitor these kind of planets over a long period of time, you can see the change in their position, and from that position you can say that okay, there is a planet in this stellar system. Okay, so other planet HR 8799 system. There are 4 planets in this system detected through 10-meter CAC in Hawaii and 8-meter Gemini telescope. These are big telescopes in one of the best sites in the world, and they use special instrument where they block the light of the star, and when they block, there is no glare, and then you can see near a faint object. Of course, then they also use the infrared imaging because these planets are cooler objects, and to monitor the cooler object, we normally use the infrared sensitive instruments. And you can see here we have the 4 planets. First planet around a star is called B, HR 8799b. So second planet around system is C, third is D, fourth is E. So according to their discovery time, they are reported as B, C, D, E, F, G, H as it is. Okay. So there are planets discovered around the star, and using this direct imaging technique, but these stars are very nearby. Okay, there are many stars which are far off, and it is really difficult to detect planets using this technique because it is difficult to detect even stars if they are very far off. So detect planets around those stars in this technique is even further difficult. So not many exoplanets can be detected through direct imaging technique. So what do the scientists do? How they detect the exoplanet? Astronomers use the indirect method to find them. Okay, where they don't see the planet directly. They don't capture the image of the planet, but they take other routes. One of them is radial velocity method. So what happens if a planet is revolving around a star? So then there is center of gravity, and star is also rotate around the center of gravity. As you must be knowing this M1R1 rule, if you have the massive body, your radius around which you are revolving is small, so center of gravity will shift towards the massive object. So in a star planet system, the center of gravity is very close to the star. Like in case of our solar system, Jupiter is most massive planet, and sun is there. So basically sun is also revolving. It is called wobbling, and wobbling around its center of gravity, which is very close to the sun because of the massive planet Jupiter. Of course there are other planets, but mass of the Jupiter is totally dominant to others. So sun also wobbles. Okay, so then it wobbles means it is going away, then coming to us, going away, coming to us, because this kind of movement is going. So if you use a spectrograph, what you will see that sometimes this light coming from sun, in this case the stars, is red shifted when it is going away and blue shifted when it is coming to us. So, and this red shift, blue shift will happen according to its orbital period. Okay. So, if we monitor these stars, for which we cannot see these planets, just we monitor these stars, we will see this wobbling. Means just take spectrograph and take their spectrum, and then you will see the light. The spectrum is moving towards red and then coming back, going to blue arcs, then coming back, going to red arcs, so on. So in this way, we can indirectly tell that okay, there is a planetary system around this star, and we can detect planets using this technique. We can say, we can determine its mass, we can determine its orbital period. As you can see, the first discovery of the exoplanet frequency B was happened due to this technique. And you can always ask why it had not happened earlier. Because we have not had that kind of sensitive instrument before that, which could measure these kind of tiny variation. Because this variation is just 50 meter per second amplitude in radial velocity. So these are tiny variation. And now we have a sensitive instrument. So just target your instrument on board to that telescope, which is mounted on the telescope, just on these kind of stars, and then you can see this variation, and one complete variation will take its orbital period, and then using this technique we have determined the mass of the 15 pack B, which was about half of Jupiter, and it was very close to the sun, and its position, as you can see in the picture, sun and Jupiter position is given there, and 51 peg B is 100 times closer to its star in comparison of the Jupiter, which is revolving around the sun. So very close by. So these kind of stars you cannot see with direct imaging. So this is the indirect method. So when you see this kind of radial velocity variation, you determine the amplitude, which is defined by k here, and which depends on its orbital period p, and mass of the planet, which is given in terms of mp sine I, where I is the inclination of the planet, and mass of the star, and then what kind of orbit it has. So E is the eccentricity, whether it is circular orbit, whether it's parabolic. So now when you do the radial velocity observation, you can determine the amplitude and mass of the star are normally known with other techniques also, and assume that you have the circular orbit, then you can determine mp sine I, which gives you mass, but because sine I, increased angle is also involved, so you determine the lower limit of the mass of these planets. Once you know this sine I value also, then this mass will increase, because the mass mp value will give you the mass of the planet. So we can determine the mp sine I, or lower limit of the mass, in this kind of system. So There is another method that is called transit method, which SD209458 was discovered in 2000. This is technique which you must have also seen. Remember the Venus transit, remember the Mercury transit. Most of you must have seen these kind of transits because there is a lot of news in the media platform, public awareness, and live telecast of these kind of events. So these kinds of transit phenomena you already see. So one can detect planet using this transit method. Now again you can ask that why we have not detected transit, means transiting planet around other stars before 2000, because these are the tiny variation. The dip you are seeing, this is very small. If you take this black dot as a Jupiter and this orange one as a Sun, so when the Jupiter passing across the disk of the Sun, the variation in the flux of the Sun is just 1%. And you know that having 1% variation of the flux in the Sun, you cannot see through the naked eye, even with a small telescope. You need very good instrument. You need big telescope to detect this change in brightness, that is 1% for the case of Jupiter around the Sun, and if it is Earth, it is even 0.0%. It is even small, very small, tiny variation. So these kind of variation you can only see through the very precise, very sensitive instrument. That's why it took such a long time. First planet discovery using this technique in 2000. And then now we have made this kind of instrument and mounted them on the big telescope, and then we determine the change in flux. What is the dip? That gives you the change in flux, delta F. And once you have the delta F, and you know the original F, what is the flux? When there is no dip, when there is no planet going in front of the star, that is normal flux. Okay? And when it is going in front of the star, there is dip. And that dip you measure, that is called delta F. Now this delta F on F0, which is the normal flux, gives you the planet radius. Once you know the radius of the star, that is denoted by R star. So for most of the nearby star, the radius is known through the other technique. So once we have this R star information, this radius of the star, we have the delta F information, we can easily determine the planet radius. Now, as you see here, when you have the Jupiter, sun system, this flux, as I said, it is just 1% variation. That is, in terms of magnitude, it is just 10 millimagnitude. With the 1 meter class telescope, we see this kind of variation in a very good sky condition. Okay, and when there is Earth kind of planet revolving around the sun-like star, this variation is 0.01%. Means if 1000 photon are coming towards you, due to this dip, you will just see 9999 photons. So just one photon difference. So this is very tiny variation, and in terms of magnitude, it is just 0.1 millimeter. And it is extremely difficult to detect these kind of variation using ground-based photometry. Okay, even on the bigger telescope, big size telescope, it is not possible to detect this kind of tiny variation. 0.01% means Earth-sized planet. Okay, so as you see here, this is the first discovery of the planet SD209458b around the star SD209458, and the tiny variation you can see here, 1% variation and 1.5% variation, and in 2.5 hour duration. So Just keep on monitoring the star. While when you do the radial velocity variation, you monitor the star for full orbital period. So, like our Earth is taking 1 year around the star. Okay. So, similarly, in these stars, orbital period is a bit larger when the planet is farther. When it is very close to its star, then orbital period will be lower, but it will be days, few tenths of days, that kind of thing. But transit duration is just in hours, 2.5 hours, because when this is going across the disk of the star. So that is a duration, transit duration, and it gives you the parameter. Like in this case, it gives that a 0.63 Jupiter mass planet is going or orbiting around a star, okay, and which has a radius of 1.27 Jupiter radius. So this is the image taken with the Kepler space telescope that is in space, as you see, and that's why you can see such a nice light curve. So when you have this kind of transit light curve, you can determine their change in brightness, which gives you the radius of the planet, okay, and using the radial velocity variation, you determine the mass of the planet. When you combine both of them, you get the mass of the planet, you get the radius of the planet or planet size, and then using these two you can determine the planet density. What is the density? Whether they are heavy or they are light, or whether they are gas giant like Jupiter or Saturn, or they are terrestrial planet like our own Earth or Mercury, Venus, Mars. So these are the terrestrial planets. So this combined information from the radial velocity and transit method gives you perfect picture of the planet. So we need both methods. Then there are gravitational microlensing technique, which is not that much popular as the other two, but here again you can find the planets. In gravitational microlensing technique, what happens that when there is a object, foreground object, and there is some light coming from background star, due to the density, due to the potential of this foreground object, light bends. It was given by Einstein in his general theory of relativity. So the bending will increase when the mass or the potential of this foreground object will be larger. So bending will keep on increasing. You make it dense object like a black hole. So you can see these kind of phenomena, and when this light bends, and now you are monitoring with your telescope and you are monitoring their light, you will see a variation in the light curve, which you can see in the left side of picture. But so if a star is in front, if star is in background, you will see this kind of Microlensing phenomena when they are in perfect alignment with you as observer, foreground and background object. But if there is a planet in around the star, and this planet around the star is in foreground, and light is coming from the background star, this foreground planet will also stop the light. It will bend the light, and you will see tiny variation in the light curve. Light curve basically the measurement of your photon as a function of time. So what we do, we keep on monitoring a star and note the time. Every few seconds or minutes we measure how many photons we have received. So we keep on noting down that flux and then plot them. So variation of this flux for different time over a long period of time, we plot it and we call it light curve. And then if there is a planet, we can see that there is tiny variation, and this kind of tiny variation gives you indication that we have a planet around a star. Okay, but this technique is not very common, not very popular, because these kind of events where you need perfect alignment between your position, your foreground object as background star, all these should be in perfect alignment, and this is not very practical. Once it happens, then star leave and you will not see the repeat observation. So once it happens, and there is no looking back. So we cannot repeat, so we cannot see those planets again. So that is a disadvantage, so that's why not very popular. Then these are the methods, various methods used to detect exoplanets, planets around the other stars. So people have used ground-based telescope to detect these exoplanets, and they have made very sensitive instrument which can measure this tiny variation, few millimeter, less than 1% variation, and in radial velocity, few tens of meter per second, that kind of radial velocity variation they can measure. But using the ground-based facilities, we could detect a limited number of extrasolar planets, that is in just few hundreds. But there are so many stars in the sky, and how to find the planet around these stars? For that, to detect planets around those stars, Kepler mission was launched in 2009 by NASA. It was pointed its direction towards the Cygnus Lyra region in sky, a very specific region, 105 square degree field. It was using just 95 centimeter diameter mirror, very small telescope, and it just pointing this telescope in a certain segment of sky, that is the, as I said, 105 square degree field of Cygnus Lyra region. It was pointing in that direction for 4 continuous years and taking pictures of this region for every 30 minutes. So we were basically measuring the flux of these stars every 30 minutes for 4 continuous years. And in this field, there were about 1,50,000 mean sequence stars. So 150,000 mean sequence star, but as I said, in sky there are billions of stars. But Kepler mission was just focusing on 150,000 mean sequence star, and Kepler was monitoring this star every 30 minutes, 4 continuously hours. So it means you have, as I said earlier, you have measurement for 4 continuous years and 1 point each 30 minutes. So then you plot this light curve and then see if there is a dip in the light curve. This is the transit method which Kepler mission was used, and it gave surprise result. Until today, 5th June 2020, Kepler and its enhanced mission, I mean, its lifetime was just for 4 years, but it was enhanced for in limited mode for few more years, that is called K2, but it was in Kepler's telescope. It has detected 2,750 exoplanets, and many of them are habitable planets. I will talk about habitable planet next slide. What are the habitable planets? But earlier, using ground-based facilities, even using the big telescope in best sky condition, in one of the best places on the earth, using the very high sensitive instrument, we were talking about a few hundreds, and here in Kepler, in very limited time, it has detected such a huge number of exoplanets. So I said Kepler has detected many habitable planets. Habitable planets or Goldilocks zone is a zone where liquid water can exist, where we can find the temperature right temperature where water can remain in its liquid form. Water can be gaseous, vapor, water can be ice, okay? But in this habitable zone, water can remain in liquid form. So as you see, the temperature between the 0 to 100 degree. So that kind of temperature, this is called habitable zone. So what scientists think that to find a Earth kind of system, we need planets residing in the habitable zone where water can exist. Okay. Of course, a planet residing in habitable zone doesn't mean that it will be Earth-like planet or it will have the water. It will have the other biomarkers, of course. So temperature in this range. Okay. So water can exist in this temperature. So there are some planets discovered by Kepler telescope which are in habitable zones, and there are long list of planets, and I will just focus just few of them. Kepler 22b is the first planet found in the habitable zone by the Kepler space mission, of course. And as you can see here, artistic picture of Kepler 22b. This is the small planet, but slightly bigger than Earth, but it is quite far away, 587 light years from Earth. Means it takes 587 light years to reach light from that planet or that star to us. These many years, 587 years to reach light from that star or the planet to us, because those star and planet Kepler 22b planet around this Kepler 22 star are very nearby. I mean, so the distance of this system, planet and star, the same for us. So this system is found in constellation of Cygnus and first planet in the habitable zone. And then later we found the Kepler 186b, first Earth-sized planet. As earlier I said, that planet was a bit bigger. Kepler 22b was bigger than the Earth, but here we found the first Earth-sized planet in the habitable zone. And as you can see in the artistic picture of the Kepler 186b, its orbit is very close to its star, unlike the solar system planets, but it is rotating in 130 days orbital period. So there are many more planets, habitable planets, discovered by Kepler in its mission, and so far we have total 4,158 exoplanets known. As I said, 2,750 detected by Kepler, but there are other missions, ground-based, space-based. So total so far 4,158 exoplanets are discovered in more than 3,000 planetary system. What does it mean that in one planetary system there are more than one planets? So around the star you can have one planet, two planets, three planets, many planets. Okay, so there are 3,000 planetary systems so far, and so far we have 37 exoplanets which are lighter than 3 Earth mass. So they are very close to our Earth, very close to Earth, not in terms of distance, but in terms of mass, very, very close. So thousands of planet candidates are still waiting for confirmation. So this number will further increase significantly in near future. So as you can see in the right side, transit method, 3,164 planets were detected, 76, more than 3/4 of the total planet discovered by transit method, and then radial velocity method, 802 planets, about 19%, gravitational microlensing, 2%, 89%, and direct imaging, as I said, is tough, so there are just 49, and then there are other methods, 1% are detected, so other methods also. So in Kepler space mission, there are three key results. So after this mission complete, we can say that there are many planets in the galaxy. There are billions of stars in the galaxy, and we can say that there are billions of the planets in the galaxy. That is our galaxy Milky Way only. There are billions of galaxies. So in each galaxy, there can be billions of planets. Okay. From the Kepler mission, we found that small sized planets are larger in numbers than the gas giants like Jupiter, etc. Okay. Here in our solar system, four are the small planets, terrestrial planets, which we call four are gas giants. But from Kepler mission, we noticed that there are plenty of small sized planets. Okay. And there are exoplanets in the habitable zone where liquid water can exist. Can exist means it is not necessary that it will exist, but we have the right temperature. If there is water, it can be in the liquid form in these habitable zone planets. So there are many exoplanets in the habitable zones. So this is the Kepler result so far. So as you can see, until 2020, we have more than 4,000 exoplanets discovered in sky, and various mass is given. I will not go in detail. So planets are discovered around every kind of star. So after the discovery of more than 4,000 exoplanets, we came to know that planets are discovered around the solar type of star like our sun. They are discovered around hot massive star where the temperature is 10,000, 15,000 degree Kelvin. Our sun is just 6,000 degree Kelvin. They are discovered around the red giant stars, not the main sequence, which is left its normal page. They are discovered around the pulsar, which are dead stars, and they are found in the multiple stellar system. So one planet is revolving around more than one star. So that kind of planets. So we have different kind of planets discovered so far. So you can see that it took thousands of years to discover all the planets around our sun, but it took only 25 years to discover more than 4,000 planets around the other stars. First discovery in 1995, normal planet around a normal star. So in last 25 years, we have more than 4,000 extrasolar planets. As you can see, this is because of the technology. We have now big telescopes. We have instruments which are very sensitive. We have telescope in space which is very high resolving power. We have big telescope in very good observing sites like Chile or Hawaii. So combining all these and combining with our effort, combined effort of scientists from various countries, we could detect these many planets around the stars. So one of the unique system so far, as I said, there are large number of stars, more than 4,000 so far, many planets in habitable zone, but one of the unique system I will give little bit detail that in 2017 we have discovered a planetary system where there were 7 planets around a sun type of star. 7 planets. We have in our solar system there are 8 planets around the sun, and here we have 7 planets around a single star. And important is not just 7 stars, because there after that in the same year one other star, Kepler 90, we found 8 planets around the Kepler 90 star. Okay, so just number is not that much important. We have these 7 planets, the terrestrial planet, Earth-like planets, Earth-sized planets. These are tiny planets. So 7 Earth-sized planets around a single star. After what we were looking, our solar system kind of thing, where we have sun and we have 8 planets revolving around the sun. We're looking for these kind of systems, and we have found one such system where we have 7 of kind of planet revolving around the star. As you can see here, TRAPPIST-1 system you can see, and you have the solar system also. Thing is that these Earth-sized planets around the TRAPPIST-1 system is they are revolving around very close system, very nearby of that star. If you see the lower picture, right side, we have the solar system where you have the Mercury, Venus, Earth, Mars. So their orbits are given. But in left side, we have the picture where all these TRAPPIST system are lying and they are revolving around the TRAPPIST-1 star. And when you zoom this system, this small region, you zoom it, you will see that there is TRAPPIST-1 system, and all these planets are there. So they are revolving very close by orbit. Even they are closer than the Mercury, much closer than the Mercury to the Sun. Okay. So TRAPPIST-1 is an ultra cool red dwarf star. So red dwarf means cool star, and slightly larger than the Jupiter. This star is slightly larger than the Jupiter, and it is located 39.6 light years away. What does it mean? That these photons which are starting its journey from this planetary system, it will take 39.6 years to reach to us. Okay, so in astronomical sense, this is very close by planetary system, but for a general public, this distance is quite huge distance, because photon which will start today from TRAPPIST-1 system, it will reach us 39.6 years later. Okay, so this is the richest set of Earth-sized planets ever found orbiting a single star, and it contains 3 planets in habitable zone also. It shows that these red dwarf stars are the most common type of star which can host planetary system. It is easier to detect planetary system around these cool stars, and the presence and composition of an atmosphere on TRAPPIST-1 system planet, its 7 planets, can be measured through infrared spectra taken during the transit. So this scientists will keep on focusing this exoplanetary system in near future with very ultra sensitive instrument. So far, as I started my lecture, planetary system beyond our solar system. Okay, whether there is any such system. So now we can say that we have many systems. Okay, so what we are looking in the future. Okay, because we have already seen habitable planets, we have seen Earth-sized planets, we have in fact seen water vapors in some planets. So what we are looking for in the future? What we, as scientists, we have to keep on looking these stars for tiny planets. We are going to discover large number of terrestrial planets and then characterize their properties, and then find how many of them are Earth-like planets, Earth-type planets where life could exist, which are habitable, where water can exist, but where presence of biomarkers is also essential, because for the existence of life we need to have like methane, water, oxygen, ozone, carbon dioxide. These are called biomarkers. So we need to have these biomarkers in the atmosphere of these terrestrial planets. Okay, so future space missions carrying large size telescopes and ultra sensitive scientific instrument will definitely help. And as you can see, in last 25 years we have gone from 0 to 4,000 plus, and We are very confident that in next few years we will have many planets which will have the conducive atmosphere for the existence of life. To do this effort, NASA is launching a lot of space missions. Not just NASA, but Europeans are also launching the missions. As you can see in the top, there are NASA missions where Hubble is already gone, Spitzer is gone, Kepler is gone. They have already done different kind of work in the planetary science. But now TESS is gone, and next year James Webb Space Telescope, which is almost 3 times bigger than Kepler, it is going to launch, and then sometime middle of next decade we will have the WFAST wide field infrared space telescope that will be launched. So once these space missions are launched, we'll be able to discover many terrestrial planets having the atmosphere for these biomarkers where the liquid water can exist, which will be habitable planets. Okay, and then there are space missions like Europeans also. They have already launched Kourou, they have launched Gaia, in Chepoj and Plato are in the planning stage. In future, they will also launch these missions. And then there are few other missions. So having all these missions in future, we are very confident that we will have a Earth type planets in sky somewhere. So my concluding remarks are few centuries. For centuries, people have been searching for other worlds like our own system, our own solar system like Sun and other planets. And we now know that there are thousands of exoplanets, and many of them are rocket exoplanets, terrestrial exoplanets. Okay, the challenge now is to find habitable planets which are similar in size and have conditions similar to our Earth, where liquid water and life might exist. Thank you very much. Now I can take a couple of your questions. First question is by Urban Gross. The exoplanets that you talked about are Earth type or Jupiter type. So I think Urban has raised this question quite early in my talk, because earlier my talk in first half of my talk, I spoke about the Jupiter type of planets, but in the later half of my talk, I talked about the Earth type of planets like tapestone system. So we have all kinds of planets, Jupiter type planets as well as Earth type planets. Other question is it possible to detect the exoplanets of solar system within the is it possible to detect the exoplanet of the solar system within the Milky Way galaxy? Of course, when we say the solar system, it means our sun and planets. So if we are saying that in the other part of the Milky Way galaxy, so these are the not the solar system, but these are the other stars. And is it it is definitely possible to detect the exoplanets around other stars in the Milky Way galaxy. And in fact, if there is just one planet, on an average one planet around a single star, there will be billions of the planet in our Milky Way galaxy itself. So having all these big telescopes with this sensitive instrument in space, we are pretty hopeful, we are pretty confident to detect them very soon. So other question is that whether we can detect them with the existing facilities at Devastal Optical Telescope. Of course, we have already detected transit. We have already detected transit variation in some of these planets using our 1.3 meter telescope Devastal. Of course, with the 3.6 meter telescope, we can do even better. So, but so far, we have observed only the known planets. But I tell you that if we can observe known planets using 1.3 meter telescope at Devastal, we can definitely discover, we can definitely detect new exoplanets using these facilities from Devastal. Okay, so yeah, the question. As question is, may I have the name of the solar system as well as name of the detected exoplanet? Of course, we have observed West 12b from the 1.3 meter telescope. A couple of papers are already published. We have observed TRESS 3 system using the 1.3 meter telescope in Devastal, and recently the paper is appeared in Astronomical Journal. Yeah. Why does the exoplanet name start with B, not A? The question is by Sana Saeed. So, see, to avoid the confusion, normally stars' name are given, but we do not give the planet the name A because sometimes A is for the star. So we, to avoid the confusion, we always give the first planet name as B, then C, then D, then E. That it keep on going like this, depending on the number of planetary system in the star. One other question by Sana Said. A Jupiter-like and an Earth-like exoplanet simultaneously passing in front of the host star, then how will we detect the small planets? We can detect them because we will monitor the photons coming out from the star, as what we do in the case of a star like TEPEST 1 or a sun where the Jupiter is passing. So a star is there, and planet, when planet is going in front of that star, we will see the dip in the light, which we call the transient light curve. So what happens when you do the model fit and you fit your light curve for this Jupiter system, then you will tell that okay, there is a Jupiter kind of planets. Now you remove from your light curve, you remove this model light curve which you have just fitted. This fit you remove from your original light curve. Now you will see the residuals. Okay. Now if there is a second planet in that system, you will find that planet in the residual of data. You fit your transit model again, and if your instrument is sensitive enough, you can detect your second planet. That could be Earth-sized planet. The same approach was taken by the TEPEST-1 system, where from the transit light curve of these planets, we detected one by one 7 planets in that system. Okay, yeah. Okay, yeah. So these are the question I've taken. If there are any more question, you please ask me later. And if someone misses today's live lecture, they can find it on ARIES Facebook page and of course on ARIES YouTube channel also. So you please subscribe to our YouTube channel, and where you can find many such lectures which you can enlighten your knowledge. You can learn a lot about the astrophysics astronomy, space science, and various technological advancement we have made in recent times. So the links to these sites is available on ARIES official site. You can also submit your questions later on and also provide your feedback by using the link available below the videos. Thank you very much.